Pluto, once considered a legitimate planet in the solar system, continues to be a dwarf planet that captivates and puzzles. Despite its proximity to Earth's prior grouping, most recent bold assertions from highly regarded astrophysicists, Neil, deGrasse Tyson, and Michio Kaku, have stirred new interest in Pluto. They have suggested that the frozen world of Pluto could be heading in the direction of a catastrophic collision with Neptune, prompting a flurry of questions about the consequences and plausibility of such a situation. Could this situation be an exaggerated theory, or is there a legitimate cause for concern? Let's explore the potential ramifications of a Pluto-Neptune collision. Initially, Pluto was classified as a planet. Due to being reclassified as a dwarf planet, its erratic orbit and this choice have kept it a topic of ongoing discussion in the world of astronomy. The most recent leading scientific studies suggest that Pluto's orbital course poses a danger, coinciding with Neptune's, sounding alarming, concerning the possibility of a fatal impact due to their proximity and respective orbits. Can a collision actually happen between Neptune and Pluto? And if so, what would the implications be? Pluto's journey around the Sun, unlike any other planet in our solar system with its own orbit, spans an intricate 248 years, which means that since its discovery in 1930, Pluto hasn't even completed one full orbit yet. But the unusual nature of Pluto's orbit doesn't end there. It continues with an elliptical path that deviates substantially from the nearly circular orbits of the majority of other planets. Pluto's orbit makes matters more difficult, tilted 17 degrees toward the ecliptic, resulting in an inclination much steeper than that of other planets' routes. An especially fascinating aspect of Pluto's orbit is its relationship to Neptune's. For about 20 years during each of Pluto's lengthy orbits, it comes closer to the Sun than Neptune, a strange anomaly that contradicts the usual positions of these two planets in our solar system. This raises the crucial question: why haven't Pluto and Neptune collided yet? The answer lies in the powerful forces of gravity exerted by other bodies in the solar system. After Pluto was discovered, astronomers quickly acknowledged the peculiarity of its orbit. In contrast to the almost flat orbits of the other planets, Pluto's steep angle and elliptical trajectory stood out clearly distinct. The difficulty of its path became even more apparent as scientists realized Pluto's orbit crosses Neptune's. Despite these unconventional traits, the orbit of Pluto has remained surprisingly stable, thanks to the gravitational effects from other celestial bodies. The problem of three bodies in celestial mechanics seeks to explain the actions and interactions of three bodies, such as Pluto, Neptune, and the Sun. Pluto's path through space can be erratic, as even the smallest changes in initial circumstances can have drastic alterations in its trajectory over long periods. On the other hand, simulations have demonstrated that the orbit of Pluto has remained steady over extended timescales, indicating that its path is not as chaotic as it may initially seem. The significant pull of gravity from Jupiter and other massive bodies serves a crucial role in stabilizing Pluto's orbit for billions of years. These forces are essential in maintaining the overall order of our solar system and preventing any potential chaos. While Pluto's orbit demonstrates an intriguing balance of chaos and stability, it's important to acknowledge the inherent difficulties. In predicting how celestial bodies will move, particularly those with irregular orbits, despite numerical simulations, orbits can provide useful insights, and they emphasize the unpredictability of space events that predict the future as uncertain. The issue raised by astronomers like Kaku and Tyson about a potential collision between Neptune and Pluto may appear remote, but their warnings have caught the public's focus. In the event such a collision were to occur, the consequences could be disastrous for our solar system. The impact would release a great deal of energy, likely the source of Pluto's destruction. Due to its small size and icy composition, the resulting debris could pose a significant risk to nearby planets and their moons, including Earth. What would happen if Pluto and Neptune collided? It would not be limited to Pluto alone. For Neptune, the collision could dramatically alter its atmosphere and orbit, depending on the nature of the incident. Michio Kaku, an acclaimed theoretical physicist, offers a unique perspective on this topic. His extensive research into string theory and celestial mechanics suggests that knowing Pluto's orbit could lead to a useful understanding of the physics. Regulating space exploration by examining gravitational interactions. Through Pluto's orbit, we can obtain crucial information for future space missions. This knowledge could help scientists better prepare for potential threats from space and contribute to the exploration of far-off areas of the solar system and beyond. The principles derived from the orbit of Pluto also have wider implications for the study of other dwarf planets and trans-Neptunian objects. Pluto's complex orbit challenges our comprehension of how planets move, pointing out to us how much more dynamic and unpredictable they are than we often perceive. The connection between celestial mechanics and string theory emphasizes the significance of understanding how planets and other celestial bodies interact. If Pluto and Neptune were to collide, it would be a landmark event in cosmology, offering a rare chance to investigate string theories based on extreme conditions, which would result in the release of a lot of energy and potentially offer a glimpse into the behavior of elementary particles and forces at high energy levels, a major focus of string theory. Although the direct impact on Earth would likely be minimal as a result of our distance from the outer solar system, broader implications for science would be profound. A collision of this kind would provide new ways to learn about the fundamental nature of the universe, especially in areas involving string theory and theoretical physics. The unusual orbit of Pluto continues to captivate the imaginations of both space enthusiasts and astronomers. The ongoing debate over its status as a dwarf planet has rekindled interest within the context of our solar system. The concerns that Tyson and Kaku raised emphasize the numerous forces that control how celestial bodies move, highlighting the importance of understanding the effects of gravity, orbital mechanics, and these forces crucial to understanding the dynamics of the ongoing debate regarding our solar system surrounding Pluto's status as a planet. The steep and elliptical orbit of Pluto's inclination defies conventional models of planetary motion. In contrast to the circular path followed by neighboring planets, Pluto's orbit, at specific points, crosses Neptune's throughout its extended trip around the Sun. The forces of gravitation exerted by Neptune and other planets have played an important part in keeping Pluto's orbit relatively constant over centuries. Despite this, predicting how celestial bodies will act in the future remains a complicated and hard-to-predict task. As a result, a Pluto-Neptune collision serves as a reminder of the inherent uncertainties in planetary dynamics. Despite the fact that such an event appears highly remote in the near future, future interactions caused by gravity between Neptune and Pluto illustrate the delicate balance that exists within our solar system. Pluto research provides important lessons for the future of space missions, helping scientists explore other distant bodies and gain a deeper understanding of planetary evolution. NASA's New Horizons mission, launched in 2006, provided groundbreaking photographs and information about Pluto and its moons during the historic pass-through in 2015. This mission revealed fascinating details about the vast areas of Pluto's surface, including massive frozen nitrogen and water ice plains, that help us learn more about the processes that shape this distant world. The New Horizons mission's success highlighted the technological advancements and collaborative efforts required to visit the farthest reaches of our solar system. By studying Pluto and its moons, scientists benefited greatly from insights into the variety of heavenly bodies and the conditions found in the solar system's outermost regions. These discoveries have profound implications for future missions, too. Investigate additional distant dwarf planets and trans-Neptunian objects that scientists can use, along with additional information about planet formation and evolution. Pluto's transformation into a dwarf planet has sparked significant discussions regarding how we define celestial bodies within our solar system. This reflects larger questions about scientific classification and the evolving nature of our understanding of astronomy. Understanding Pluto's orbit is essential for insights into celestial mechanics and planetary dynamics, especially as we venture further out into the wilderness of the solar system. Through Pluto's investigation, interactions with other planets and celestial objects, particularly Neptune, keep expanding our understanding of the formation and development of planetary systems. Pluto's discovery and ongoing study have significantly influenced our understanding of planetary motion and the development of a region known as the Kuiper Belt beyond Neptune, where tiny icy bodies reside. Understanding Pluto's orbit provides valuable clues about the gravitational interactions that may have shaped the early solar system, offering essential data for future space missions that emphasize exploration. Outside of potentially habitable worlds in our solar system, despite the possibility of a Pluto-Neptune collision being extremely unlikely, research into these celestial objects serves as a reminder of the universe's ever-changing nature as we carry on our exploration of the far reaches of our solar system. And beyond, the study of the orbits of planets and celestial mechanics will continue to be important to our efforts to explore Pluto. The unique orbit provides useful lessons about the planet's complexities, the forces that shape motion, and celestial bodies throughout history. The ongoing investigation of Pluto's orbit and encounters with Neptune serves as a reminder of the erratic nature of the universe. With each new discovery and theoretical model, we enhance our comprehension of the universe and gain insights into the enigmas of far worlds. The study of Pluto's orbit not only provides answers about this distant world, but also helps us predict future changes in the way the heavens work, assisting in better comprehension of the forces that govern our solar system and beyond. The possibility of a collision between Pluto and Neptune, though highly unlikely, underscores the universe's dynamic nature. The research of Pluto's orbit, its interactions with Neptune, and the gravitational forces at play offer valuable insights into celestial mechanics. As we continue to investigate these far-off objects, we refine our models of planetary systems and enhance our capacity for forecasting future cosmic events. Possibilities for discoveries in this field are countless, and as technology advances, so too will our capacity to comprehend and study the vast and ever-evolving universe. The investigation of Pluto's position within our solar system will continue to shape our understanding of the universe for years to come. Pluto's orbital behavior, with its distinctive interactions with Neptune, has fascinated the scientific community for a very long time. Despite its designation as a dwarf planet, Pluto continues to challenge our comprehension of planetary dynamics. The fact that Pluto's orbit coincides with Neptune's at various points without resulting in a collision highlights the complicated nature of gravity. One of the most intriguing features of our solar system's mechanics, one of the most intriguing features of Pluto's orbit is its resonance with Neptune. This resonance, where Pluto completes 2 orbits around the Sun for every 3 orbits Neptune completes, ensures they never get too close to each other, even though their paths cross. In this resonance, Pluto and Neptune are basically enmeshed in a cosmic dance where their orbits are set in such a way that they never collide. This unique gravitational relationship is an excellent example of the precision and balance that exists in celestial mechanics. The forces exerted by Pluto's gravity and that of Neptune, and vice versa, collaborate to keep a stable orbit for both. In the absence of this resonance, Pluto's orbit could have been disrupted, possibly resulting in a collision or other significant perturbations in its trajectory. Acknowledging this, astronomers need to communicate with each other as it provides insight into how celestial bodies are able to remain stable, even though their paths appear to be jumbled at first glance. The Kuiper Belt, beyond Neptune, is a treasure trove of icy bodies and dwarf planets. Pluto is the largest known object in this belt. Its orbit provides useful information regarding the circumstances that prevail in this faraway region of the solar system. Kuiper Belt objects KBOs and trans-Neptunian objects TNOs are remnants of the solar system, and their research enables us to gain a peek into the conditions that existed during the solar system's formation billions of years ago. Space agencies like NASA are now directing missions toward research in these far-flung regions. NASA's New Horizons mission, which carried out a 2015 flyby of Pluto, provided us with previously unseen images and data about Pluto's surface and atmosphere. The mission's findings revealed towering frozen nitrogen plains, ice mountains, and a complex weather system, suggesting that Pluto is a world that is active geologically. The diversity of the dwarf planet's moons reveals clues about the formation and evolution of moons in the outer solar system. The New Horizons mission also demonstrated the expanding capabilities of contemporary space exploration. Such missions not only expand our knowledge of distant celestial objects like Pluto, but also set the stage for greater ambition and research into the Kuiper Belt and beyond. The success of this mission has rekindled interest in exploring these faraway regions and may elicit similar tasks for other objects contained within the belt. Despite the apparent stability of Pluto's orbit, its tilted and eccentric trajectory raises concerns regarding the long-term dynamics of the solar system. The fact that Pluto's orbit differs so much from the nearly circular orbits of the 8 major planets offers astronomers a fascinating puzzle. The inclined and elliptical shape of Pluto's orbit serves as a reminder that our solar system doesn't work as neatly as it might seem. The chaotic behavior exhibited by Pluto's orbit could have significant effects on our comprehension of planet formation and evolution.